Welcome back in this course on polymer chemistry, and in this lecture today we are continuing our discussion which is left over from last lecture on frictional properties of polymers in dilute solution, and then we will begin a very important discussion on polymer characterization, which is basically how to determine polymer molecular weight. We plan to give just an overview of the techniques which can be used for polymer determination of polymer molecular weight today, and if time permits we will continue and discuss the method of dilute solution viscometry by which we can determine viscosity average molecular weight. Now, let us continue the discussion we are having in last lecture. Now, as we understand in last lecture that most of the polymer chains are flexible, and when they are dissolved in solution and they are moved in solution, they actually carry the solvent molecules which are attached to the polymer coil. They moves along with the polymer coil. So, we can imagine a equivalent sphere which contains the polymer chain and the solvent molecules as a impermeable hard sphere, and for that hard sphere we know that Einstein equation of viscosity is given by this expression, where eta and eta 0 is the viscosities for the suspension and suspension medium, which is basically a polymer solution, and the solventing medium or the solvent. Now, it can be easily shown to have this expression. Let me show that phi 2 is the volume fraction, which is given by volume of polymer divided by total volume. This is total volume. Volume of polymer is given by number of polymer molecules VH. VH is the number of volume of one polymer, hydrodynamic volume of one polymer coil, hydrodynamic volume of one polymer coil. It is basically the sphere which I showed in last one, the polymer chain plus the solvent molecules which moves along with the polymer coil, and you can imagine a equivalent sphere. So, that the VH is the volume of that sphere divided by total volume is the number of particle, which is Avogadro number multiplied by moles of polymer VH by total volume Na. Now, number of polymer and moles of polymers can be expressed by mass of the polymer divided by the molecular weight of the polymer VH by total volume, which gives M by V NaVH by M. M by V is the concentration, C concentration in mass per unit volume. So, we can write this as C by M NaVH. Okay. And eta Sp, you know, if you recollect, eta Sp is eta r minus 1 eta by eta 0 minus 1. So, you can directly write this expression from this. I can rearrange it, because intrinsic viscosity is given by limit c tends to 0 eta S p by c, which is basically given by Na eta S p by c, which is you can write from here, you divide by c and you get this expression. Now, what does it mean? It means that intrinsic viscosity is proportional to Vh by m. Vh by m is volume by mass of the polymer coil. Okay. This is the volume of a polymer coil, one polymer coil, and this is the molecular weight, that means mass of one polymer coil. That means intrinsic viscosity relates to the inversely to the density, it is inverse to the density of the random coil. So, denser the coil volume, smaller the intrinsic viscosity, as we have been discussing earlier, that if the coil becomes more dense, then smaller is the size and smaller is the intrinsic viscosity for the same molecular weight. If the chain has same molecular weight, but lower VH, lower size, more compact coil, which we can imagine for a applicable, or which is we will get for branch polymer. As we discussed, for branch polymer, for if you compare between linear and a branch polymer from same molecular weight, the branch will have more compact volume. So, it will have more lower hydrodynamic volume per coil. So, in that case intrinsic viscosity would be smaller. Now, another information this expression gives is that the term intrinsic viscosity multiplied by the molecular weight is given by this, which is only depend upon the volume of the polymer coil in the solution. So, intrinsic viscosity does not depend only on the volume, okay. It depends on inverse of the density, but if you have intrinsic viscosity multiplied by the molecular weight, then intrinsic viscosity only this term, the intrinsic viscosity multiplied m depends only on the hydrodynamic volume. So, if there are two hydrodynamic chains having same hydrodynamic volume, irrespective of their chemical and structural difference, the product of intrinsic viscosity and the molecular weight will be the same. Okay. If the two coils, polymer coils, have same volume, hydrodynamic volume, then irrespective of their chemical and structural difference, the product of intrinsic viscosity and molecular weight will be same. Now, just the same information which we discussed, we can compare between a branched chain and a linear chain. These are the yellow ones are the branched of this linear polymer. This, imagine these two have same molecular weight. If these two have same molecular weight, obviously if you have branches, then it will have more compact structure. So, hydrodynamic volume will be lower in this case. So, molecular weight is m, in this case molecular weight is also m. So, hydrodynamic volume is higher in this case, hydrodynamic volume is lower in this case, segmental density of the coil is lower, segmental density is higher. So, intrinsic viscosity of this will be higher than the intrinsic viscosity of the branched polymer chain have same molecular weight, and if you divide branch by the linear, the value of the branch intrinsic viscosity by the linear one, you can get the extent of branching in this polymer coil. Now, we will further treat this expression and see whether we can arrive at expression which can help us in determining the molecular weight by dilute solution viscometry. we have not started discussion on molecular weight determination. So, this is probably inappropriate, this title is inappropriate at this moment. So, you can just ignore this title for this moment and just concentrate on the mathematical part of this expression. We have got this earlier. So, this was written VH, now we are writing V, but you can consider this as VH. So, I am writing this. Now, VH is the volume of the particle. This is the volume of this particle. Now, remember we will discussing the radius of gyration. We discussed that the radius of gyration is almost like the radius of that sphere. So, this radius of gyration would be related proportional to the actual radius of this hydrodynamic polymer coil. So, the volume VH would be proportional to the R cube, volume given by 4/3 pi r square, R is this R. Now, this R we said it is proportional to the radius of gyration. If you can recollect our discussion in the definition of radius and gyration, these are very close. So, we can write that VH is proportional, the proportionality sign is missing here. VH is proportional to the radius of gyration to the power 3, and radius of gyration can be written as the expansion factor and the radiation gyration for the arm part of chain. So, we can write that intrinsic viscosity is proportional to, the proportionality sign is also missing here, is VH, which is proportional to this term divided by m. Now, this we can remove this proportionality by applying or introducing a constant. This is a constant. So, we can write intrinsic viscosity is equals to this term. Okay. Remember, this should be H, because we have mentioned H in the last lecture. So, these are all H, VH, extension factor H. So, this is the expansion factor because of the solvent, polymer solvent interaction. This is expansion happened due to, because the polymer coil is in solvent. We can rearrange this expression and write this, which is just a mathematical rearrangement. You can write this. Now, what is if you recollect, this was proportional to n to the power half, which is proportional to molecular into half, okay, which means 3 by 2 divided by m 3 by 2 would be some constant term, okay, because these two are proportional. So, what we are doing here, this is a constant as we just discussed, this is also constant, and we are clubbing these two in another constant, and you have the expansion factor and molecular weight to the power half. This expression is known as Claude-Fox equation, and remember, as we said, this expansion factor is for large expansion, it was proportional to n to the power 1/10. Remember, we just discussed here in last lecture, which is means this is not exactly, but it is approximately proportional to n over 10. So, it is approximately proportional to n m to the power 10. So, you can now write, you can express this in terms of molecular weight and then couple those two and write k is m to the power a. This expression we got from the theoretical calculation which we just carried out, but it was before this theoretical expression was arrived by Claude-Fox. Mark-Houwink has actually arrived to this expression semi empirically by experimentally. So, this expression is known as Mark-Houwink equation. This equation later we will use for determining molecular weight by dilute solution viscometry. So, please remember this expression where k is constant and a is also constant. We will learn more about k and a in when we discuss the solution determination of molecular in solution viscometry, or you can now complete that discussion. So, as I said that Mark-Houwink equation derived before Claude-Fox equation as an empirical equation. Now, k and a are constant as we just discussed while deriving this expression, and it is there is constant for a given polymer solvent temperature system. So, if you change any of these three, polymer solvent and temperature, then k and a value will be changed. So, this is only constant if you have same polymer solvent temperature, because if you change on either of them, VH, the coil dimension will change and your gyration radius of the expansion factor will also change. So, these values also will change. Normally, A lies between 0.5 to 0.8 for linear chains, and if you have very steep chains like rod like, then A can move up to 1, but for linear flexible chains it will be between 0.5 to 0.8. And for theta condition, what we have seen earlier, for theta condition, what is the value of AS for or expansion factor for theta condition? If you seen, it was for 1. So, if this is 1, then for theta conditions the A value would be 0.5. So, it is same as if there was no expansion of the coil due to the presence of the solvent. Now, A increases as the coil expansion occurs in good solvent. In good solvent, the coil expands. So, the value of expansion factor becomes more than 1. So, the A value becomes more than 0.5. Now, K increases with the value of A for flexible. Typically, you have seen, it has been seen that K also increases with the increase in the value of A, and it is typically around this range. A is more informative in polymer while you will find that A is probably more important than between these two constant. Now, for branch polymer, obviously even if you consider theta condition and put a branch polymer, then the expansion factor will be lower than 1 if you compare with a linear polymer. So, your A value could be lower than 0.5. For a linear polymer, A can never go down below 0.5, but if you have a branch polymer, it is more compact. So, expansion factor will be, if you compare the expansion factor of unperturbed linear polymer chain, it may go down below that, below 1. So, you will the intrinsic viscosity would be smaller as A becomes smaller. Now, this expression becomes little more complicated when you have copolymers, you are characterizing copolymers. As I said, we will use this expression Mark-Houwink equation when we will try to determine the molecular, we will discuss the determination of molecular weight of polymer chain by viscosity method. Now, let us start our a very important discussion on how to determine the molecular weight. And at the beginning, what I would like to do, I will just to give you an overview of the techniques which are available and used to determine the molecular weight. These are the different techniques, and what I have just listed the principles, and some of these techniques are absolute techniques. That means, you do not require any calibration by the polymers of known molecular weight. Actually, you can divide in these techniques into two types. One is absolute molecular weight determination, where you do not require any calibration curve a priori by known polymer molecular weights, and there are relative methods where you will actually require a calibration curve by known polymer molecular weight, where the molecular weight has been determined by these absolute techniques. We will discuss the principle and the other things, the process, while indeed we will discuss these techniques individually. So, time being, we are not spending much time on these techniques. So, what we will do, again this is a continuation of the list we have, and we will spend significant of time on the techniques which are used very frequently in the labs, like gel permeation chromatography, light scattering technique, dilute solution viscometry, and in group analysis and membrane osmometry. These techniques, membrane osmometry, first 4 techniques are based on colligative property. So, the principles are similar. So, if you discuss or if you understand one of them, the rest will be clear to you, and this all gives, because colligative property is based on gives the number average molecular weight. So, this all gives number average molecular weight. In spite of instead of spending more time on this table, which we will discuss in more detail when we discuss the individual techniques. Let us move to the actual techniques. Now, let us, because we are having the discussion on Mark-Houwink equation, let us start the method or the techniques which uses dilute solution viscometry. Now, we have seen that we have seen that this is the expression for dilute polymers, the intrinsic viscosity of polymers in dilute polymer solution, and what I can find out this intrinsic viscosity is K by m. Now, as the technique suggests, this is using the dilute solution viscometry. So, the molecular weight gives is mv, where mv is viscosity average molecular weight. We will just in a minute we will deduce what the expression for viscosity average molecular weight. In dilute polymer solution, we can assume the following in reasonably well, these assumptions are reasonably okay to do. Is one, the eta specific viscosity is given by the summation of the specific viscosity of the individual chains. Now, in as you know that in real polymer mixtures there are numerous polymer chains having different molecular weights. So, the intrinsic, these are the assumptions we are making, that specific viscosity can be obtained by summing up the specific viscosity of the individual polymer chain. Second, the specific viscosity of the individual chains can be obtained by this expression. Because we know that limit c tends to 0, eta Sp by c is your intrinsic viscosity. So, if the solution is very dilute, then we can write eta Sp I is C I eta I. Third is the intrinsic viscosity of the ith chain is given by K A my A. That means, this what we are assuming, that K and A values are independent of the size of the molecule. So, eta Sp I is the intrinsic viscosity of Ni moles of molecules having molecular weight Mi present at a concentration of Ci per unit volume. So, Ci can be written as Ni is the number of molecule, Mi is the molecular weight of that molecule. So, this gives you total mass of the ith molecule divided by volume. So, this gives your concentration in terms of mass by volume. So, we have these three assumptions, and which is reasonably fair if we deal with dilute polymer solution. So, now we can find out the expression for the intrinsic viscosity for the polymer sample, which is the mixture of all the polymer chain, which is given by limit c tends to 0 eta specific by c. Eta specific is given by summation of I and C we can continue to write this is as summation of eta I C I by C you can write the value for C I N I M I by V, and C is basically summation of C I. So, you can write N I M I by V. N I is K M I. So, I can write, let me write in a separate page. N I is given by if I can take out K outside this summation, now we can write. So, you get this expression, this is for ultimately the expression for, we started from this intrinsic viscosity and we did all these steps and finally reached here. Now, intrinsic viscosity this key machine. So, if you compare these two expression, then we can, this MV is so you get this expression. So, in the expression of this MV, we just found out that it is having the expression of this. Okay. If A is 1, which we just discussed, it is for highly elongated rod like molecule, then MV would be same as MW. Okay. If A is 1, it will be NIMI square by NIMI. So, it will be equals to MW, as A value lies between 0.5 to 0.8, MW will be MV would be more than Mn and less than mw. Let me write in a fresh paper. mv is given by as A is between 0.5 to 0.8, mv will lie between mn and mw, and it will be much more closer towards mw if A is higher. If the coil expand, then it will be the more expansion, the more closer to mw, and for highly stiff rods where A is 1, mv becomes equal to mw. So, now we have we know K is intrinsic viscosity is mv by A. Okay. Now, we know we just got the expression for mv, which is given here. Okay. This is the expression for mv. So, from here if you plot, so how to get the value for mv? If you know K and A, if K and A are known, obviously you can find experimentally the value of intrinsic viscosity, and then if you know K and A value, then you will be able to find the value for mv. What happened if K and A are not known? Then you can find, you take log eta and plot with log mv, you take log is equal to log K plus A log mv. So, if you plot log of intrinsic viscosity with log of viscosity average molecular weight, the intercept will give you log K and the slope will give you A. Okay. So, what you need to find out? You need, if you know from experiment or if you know from literature in the book, you are fine. You can get you can determine experimentally the value for intrinsic viscosity, and you can utilize this expression to get the viscosity average molecular weight. But if you do not know, somebody has done it before, means for unknown sample, if the unknown sample this K and are not listed, for unknown sample, then how do you determine the viscosity average molecular weight? Then what you need to do? You need to plot log of intrinsic viscosity with many known molecular weight, and then get the you do experiment, take 5 to 10 samples and make dilute solutions from that and determine intrinsic viscosity and plot this to get log K and A. Now, question is here, you need to plot log mv, okay, that is what you need to determine. If you are plotting here log mv, now you are again targeting mv for the unknown molecules. So, how do you, then you do not know the mv for, this is a calibration curve which you are getting by doing experiments of intrinsic viscosity measurement of many polymer molecular of known molecular weight. Okay. Now, known molecular weight can be either Mn or Mw, which you already determined by the absolute techniques. Okay. Let me come back and say it again. If K and A are not known, what you need to do, you make say 5 solutions of 5 different molecular weight M1, M2, M3, M4, M5, and then measure the intrinsic viscosity for these eta 2, eta 3, eta 4, eta 5, and then plot log of eta versus log of m and get log of k and a. Now, actually this is supposed to be mv. The expression gives you k is eta is k mv to the power a. Okay. So, ideally you should have mv value for all these samples, which you do not have, because that is what you are determining. So, what samples you will use for calibration, where mv is much closer to any of the known molecular weights mn and mw. Now, if you have very narrow dispersed polymer, then you can consider mw or mn is same as mv. If you have very narrow dispersed polymer, then mw are very close to mv. So, you can take those mws and use here and do the calibration curve. So, if your k is a and not known, you need to have 5 different molecular weight of that solution, where the molecular weights are known by other absolute techniques, and the samples should be such that they are very narrowly dispersed, so that mn or mw can be equated to the mv. So, that is the reason it is a relative method, it is not absolute method. You cannot determine mv for a unknown polymer by as such. You need to have a calibration curve, and for doing calibration curve you need to have 5, 6, 7, 8 known molecular weight narrow dispersed same polymer, whose molecular weight you need to get it from the other absolute techniques like osmotic pressure or light scattering techniques. Then you can determine the viscosity average molecular weight of the unknown sample, which k and a is not known in the literature. So, all this case we said that we determine the intrinsic viscosity. Now, how will you determine for a given polymer sample in a solvent for a particular temperature? How will you determine eta, intrinsic viscosity? Eta is given by limit c tends to 0 eta Sp by C. Now, if for a dilute solution the plot of eta Sp versus C is linear only till your eta r is less than equals to 2. Okay. So, if your eta value of the solution is twice 2x the eta 0 maximum, then you can find out that eta Sp is linearly related with the concentration term. So, we can write the eta Sp is linearly related to C concentration only till eta r is less than 2. So, eta Sp by C can be written as this is the slope of that linear relationship between eta Sp by C with C, and that is only applicable till eta r is less than 2. Now, this k, the slope depends on the molecular weight of polymer, it is not equal for all the lengths of polymer. Okay. So, we need to find out something else where that constant can be applied to any of the molecular weight of the polymer chains. So, Huggins found out that K versus eta square is linear and pass through origin. K is the slope. So, we can write d eta Sp by C by dC, this is the slope K, that is proportional linear. So, I can put another constant k 1 and eta square, okay, because there is no constant term, because this is passing, it passes through the origin. Okay. Now, you can integrate this, you integrate this, you get C is equal to eta 1 . Now, because Huggins has established this relationship, sometimes this k 1 is written as k h. So, eta Sp by C is written as plus k h eta square C, this is Huggins constant. This is Huggins equations. Now, this is constant for a particular polymer solvent temperature system. You change any of these you change any of these three, polymer, solvent or temperature, it will vary, the value of K h will vary, it is of course independent of MW of the polymer. So, now you can use this for the mixture of polymer or the interpolymer distribution, so that you can it can be useful because it is independent of the molecular weight. Now, for if the concentration is little higher, we talked about this is only applicable for eta r is less than equals to 2. If the concentration is higher, then it can, this expression can be expressed like the virial expression, where plus other constant so on. If eta C is less than, much less than 1, you can ignore these terms, higher term C square onwards terms, then you can end up getting the Huggins expression again. So, only in case of dilute solution you can consider only this up to this, these higher terms you can neglect. K h have value between 0.3 for good solvent to 0.5 for poor solvent. Now, in this case, from this expression, Huggins equation, you only need the value of Kh. Okay. If this is known, if Kh is known, then obviously you can determine intrinsic viscosity by plotting eta Sp by C versus C till the C is very dilute, C should not be very high. So, the solution remains dilute, then you can get the expression for eta from the intercept, and if you know Kh, then you can get the expression, you can get the value of molecular weight directly. If you know Kh, you also will know intrinsic viscosity, then you know from the expression you can get that molecular weight. Now, alternatively, we can use the inherent viscosity, which can be expressed in specific viscosity, and specific viscosity is much lower than 1. This expression can be written as eta Sp minus half eta square. So, this Huggins equation can now be written as directly eta r is equals to C plus So, this gives a similar expression like the Huggins expression, but it is in terms of the inherent viscosity, and this is this expression, this constant is named at the person who has given this. This is Cramer's equation, where K is Kh minus half. So, it will be a negative quantity. So, now we have two expression, Huggins equation and Cramer's equation. So, you can plot eta Sp or this term inherent viscosity with respect to C, and then from slope and the intercept you can get the value of intrinsic viscosity. So, I can plot either eta reduced, which is nothing but eta Sp by C, or we can plot eta inherent, which is ln eta r by C, and we will get, in case of Cramer, that constant is negative, we just saw. In case of Cramer, this is negative, so slope will be negative, and in case of Huggins, this is positive, the slope will be positive. So, this will be eta reduced, plot for eta reduced, and the other one will be plot for eta inherent. So, from this you can get the value of the intrinsic viscosity. Okay. So, in summary, if we know this Mark-Houwink equation, where mv expression we have seen. Now, using either this Huggins equation or Cramer equation, you can plot either the reduced viscosity or the inherent viscosity with the concentration term to get the experimentally the intrinsic viscosity. So, this is in your hand. You can make solutions of different concentration and you can measure viscosity of the solvent and viscosity of the solution, and from viscosity of the solution and solvent you get relative viscosity, or from there you get specific viscosity, and from there you get reduced viscosity and inherent viscosity. So, these are all in your hand. You can get a viscometer, and typically the viscosity is measured by passing using this defined viscometer, where the solvent and the solution is passed through capillary, where the time is proportional to the viscosity. So, basically if you measure the time of efflux time of the solution and the solvent, from the ratio you can get the relative viscosity, and from that you can get the reduced viscosity and inherent viscosity. So, basically you plot, you make different solutions of different concentration and plot with this, you get the intrinsic viscosity. So, once you know this, if you know K and A, you can use this expression to find out mv. As you have seen, if you know the Kh or the Kk, the Huggins constant or the Cramer's constant, Kh or Kk, then only one concentration itself you can get the value of intrinsic viscosity, the molecular weight. And if you do not know this K or an A and the Kh or Kk, then the process is to determine very some or few very narrowly dispersed same polymer and get the absolute molecular weight from any other techniques, and because it has to be very narrow dispersed polymer, you can take any of the main or MW as equals to MV, and you find out the intrinsic viscosity for say one polymer, and then by plotting log intrinsic viscosity versus log molecular weight, you can get K and A value. From that you can get this MV. So, with this we conclude the discussion on determination of molecular weight by viscosity method. Remember, whatever we are doing in this determination, there are few precautions you have to take. You have to make the solution to determine the intrinsic viscosity such that the concentration of the solutions is very low. It must be in dilute solution, very dilute solution region, and also you need to remember that relative number in this method you cannot get a measurement for a unknown polymer as such. It is not absolute method, it is a relative method. So, what we will do in the next lecture, we will start discussing about the other methods of determining molecular weight, namely Mn, Mw and other polymer solvent interaction parameters.